In the name of God. Hello, dear students. Welcome to Ferhwa's website. My name is Masoud. I'm a physics teacher. I'm at your service to explain physics curriculum, grade 12. We are in chapter 1, and I'm gonna explain a new subject, which is angular quantities versus linear quantities. We wanna compare the rotational and, let's say, linear quantities with one another. I prepared the table for you, and we have this table actually in our textbook. Rotational, the title of the table is rotational and linear kinematic equation. Rotational and linear kinematic. Actually, kinematic means anything that is related to motion. Kinematic means comes from kinetic, right? Kinematic equation means anything that is related to kinetic, let's say energy, or anything that's related to motion. The first column is dedicated for rotational equation. The second column is related to the linear equation, and the linear equation, if you take a look at these equations, they are not, let's say, we are familiar with these equations. So far we, let's say, got them in details, especially in grade 11. We got information, a lot of information about these equations. That's why, but for any linear equation, there is a twin in rotational motion, right? There's an analogy. There's an analogous equation for linear motion in rotational motion, right? So let me read the first equation, and it's twin in rotational motion. For example, this is actually the old equation. Vf is equal to Vi plus A delta T. Final velocity is equal to initial velocity plus A delta T. This is the linear equation, actually the first linear equation in, right, the first linear equation. So what's the rotational twin for this equation? This one, omega F means final angular speed is equal to initial angular speed plus alpha delta T. Omega final is equal to omega initial plus alpha delta T, right? If you, let's say, look at these equations, they are, let's say, I can see they are copy-paste. They are copy-paste for one another, except for the quantities, except for the physical quantity. This one, V means, let's say, velocity in linear motion. But here we have omega, means velocity in rotational motion. This one, for example, V, yeah, we talked about V and omega. A, we have acceleration, linear acceleration in linear motion. We have alpha means angular acceleration in rotational motion. And delta T is the same, right? So they are, I can say, they look alike, right? Except for in the form of the equation, right? They have the same form. They have the same form, but let's say different physical quantities. The second equation, delta x is equal to initial velocity multiplied by delta t plus 1 over 2a delta t squared. Delta x means, yeah, guess this physical quantity. What's this? Means linear displacement. What's the, let's say, twin of this quantity? Delta theta. Delta theta means let's say angular displacement. So delta x, let's say, has a rotational twin, which is delta theta. V has a rotational twin, which is omega, and alpha, alpha for A, right? So the equation for the second equation for rotational motion, delta theta is equal to omega initial delta t plus 1 over 2 alpha delta t squared. The third equation let's say V final square is equal to V initial square plus 2A delta X. So the same thing, right, we have it in the rotational motion except for the quantities, right? I told you, they have the same form, but different, let's say, physical quantities. Omega final square is equal to omega initial square plus 2 alpha delta theta. And the last one, delta x is equal to 1 over 2, let's say Vi plus Vf multiplied by delta t. Actually, Vi plus Vf they are inside the bracket. Delta theta is equal to 1 over 2, bracket, Vi plus Vf, we close the bracket, delta t. Right? They are equations. Actually, I told you this column, it's a background for us. We know these equations. Actually, we got information about these equations. They are not, let's say, strange for us. We are familiar with these equations, but they are new for us. They are new. We focus on these equations. Sometimes we need the right column, no problem. And for memorizing, I have a suggestion for you. For memorizing the new equations, let's say we need the older equations, right? That's why they are helpful for memorizing the new equations, and even they are helpful for understanding the concept of rotational motion. I can say they are edit. These equations are edits of what? Are edits of the, let's say, linear version, let's say, equation version. I wrote some hints for you. Let me read them for you. Let me pull it up for you for better, let's say, seeing the title and the hint. Hint number 1, it says, equations above, equations that we talked about it, are applied only for objects rotating about a fixed axis. So these equations, kinematic equations, I'm talking about the rotational kinematic equations with constant angular acceleration, with constant alpha. I'm talking about the rotational form of the equation. We concentrate on the rotational form, not the linear form, because linear form, I told you, they are older equations. We got information about them in grade 11. So rotational equations are applied only for the cases that we have the fixed, let's say, axis. Like what? Teacher, give me an example about the fixed axis, the object with the fixed axis, like rotating, for example, Ferris wheel, rotating tire. They are all, let's say, fixed axis. They have fixed axis actually, axis. But what do you say about this one? So I want to rotate this marker, right? Whenever you rotate this marker, let's say, rotates and changes its position, let's say, gradually. So in this situation, this object, the rotating marker, does not have any fixed, let's say, fixed axis. That's why we cannot apply these equations even for this marker, right? Because the axis of rotation is, let's say, changing continually, right? So hint number 2, omega in the equations above stands for the instantaneous angular speed, not the average angular speed. So omega represents what? Omega stands for instantaneous angular speed, not the average angular speed. Instantaneous means you can, let's say, measure it at any instant, at any moment, not the average angular speed, right? So, for example, if I say omega, one equation, omega f is equal to omega I plus alpha delta t. So omega let's say these values of omega couldn't be average, let's say average value, because you mentioned that this speed, this angular speed, is for the first, for the starting, for example, starting situation. You say omega f. You mentioned that, let's say exactly. You say final angular speed. But whenever you say omega lonely without any subscript, or omega average, if you say omega average, so it differs from the omega I and omega f, because omega I and omega f are, let's say, are velocities at different moments. But this one, omega average, means it's a constant, let's say, speed, right? It's a constant speed during the whole motion. So this is the difference between instantaneous omega, instantaneous angular speed, and average angular speed. Keep in mind that average, let's say, angular speed is a constant value, right? And we don't include omega average in these equations, right? So omega average does not belong to the kinematic equations with constant acceleration, because it has only one value. You cannot determine, for example, omega I and omega f. That's why it doesn't apply on omega average. Hint number 3, every linear quantity has a corresponding twin. I explained it for you, actually. I mentioned it, let's say, in advance for you. Every linear quantity, what are the linear quantity? Let's say, think about it. They are x or delta x, displacement, velocity, and let's say displacement, velocity, and acceleration, right? They are displacement, velocity, acceleration. They are linear quantities, right? It says for any linear quantity has a corresponding twin, has a rotational twin, let's say in rotational motion, corresponding twin in rotation. So what's the corresponding twin of x, theta? What's the rotational twin for v, omega, and what's the corresponding, let's say, rotational twin for a, means alpha? So it's, let's say, it helps you to, let's say, to replace the linear equation, the linear quantities with the rotational quantities, right? Let's move on to another subject. So what's the other subject? We have a sample problem, but I'm gonna, let's say, finish this lecture here. Thank you very much for watching this video, and take care.